Right, so it's top of the hour, so let's go ahead and get started. I would like to invite you all to this fourth meeting of the Forum for Implementation of Reliability Standards for Transmission, or i2X first. We are in season 2 now, so that's why the fourth meeting of the season. Yeah. Usual stuff, the first half of the meeting will be recorded and will be posted on the ESIG website. So if you don't wish your voice to be recorded or your video to be there, please turn your camera off and mute your mic. Again, the goal and outcomes for i2X first overall. This whole initiative is initialized by DOE and supported by Department of Energy, and it is to facilitate understanding and adoption of new and recently updated standards that are relevant to existing and newly interconnecting wind, solar, and battery energy plants. We convene industry stakeholders to enable practical and more harmonized implementation of these interconnection standards. In our meetings, we discuss these issues and then produce summary of the meeting capturing recommended best practices, challenges, and gaps that require future work. Just a few words about the leadership team. We have Cynthia Boswell from Boston Government Services, contractor for DOE Veto Office. Robert Reedy from Lindo Reed, contractor for DOE Solar Office. Will Gorman from LBNL. Jens Boemer from EPRI, myself, Julia Matevosyan from Energy Systems Integration Group, or ESIG, and Ryan Quint from Elevate Energy Consulting. So just a quick summary of the last meeting. So that was third meeting of the second season of i2X first. We focused on inverter-based resource plant design evaluation. So basically, what do you need to do to make sure that plant as designed conforms with applicable interconnection requirements, including IEEE 2800, if those are requirements that apply in the area. So the first presentation in the meeting was IBR Plant Design Evaluation overview, where Jens Boemer from EPRI went through IEEE P2800.2 draft on this topic. So again, IEEE 2800.2 is best practices for conformity assessment of IBR plants and in conformity with IEEE 2800 standard. And we're currently drafting the standard. It's going through industry pilot at the moment. And then we had a developer perspective on design evaluation. So we heard from Rishi Maharaj from ENGIE and Patrick Hart from EPC contractor perspective. We had Q&A structured discussion around the questions of design evaluation. And then recording has been posted and presentations are there as well, and the meeting summary too. So if you missed the meeting, probably the best thing is to look at the summary first and then go back to the recording of the presentations. So just a few key themes from last meeting. It's necessary to cross-coordinate amongst all involved parties in plant design. So OEMs, EPCs, consultants, and project developers, they all need to work together to avoid non-conformity and any delays and performance issues after the plant have been commissioned. There needs to be a proactive approach, bake high bar compliance into contracts and processes to prevent missed requirements. So Rishi specifically talked about importance of contracts between different consultants that work on the project, between OEMs, to make sure that every questions that consultants and developers have are answered by OEMs, and then any questions that developer has are addressed by consultants, and interconnection requirements and the applicability gets into the process as soon as possible. There is a need for standardization, so we need to use consistent data format, simulation procedures, model verification to reduce errors and enable automation. Specifically, Patrick talked about power plant controller related risks. There is a need to deliver and validate power plant controllers early to make sure that they are properly modeled, that power plant controllers are type tested in a similar way as inverters get type tested. And so that improves product level certification and then integration into the project as the project plan, specific plant design is happening. There needs to be continuous evaluation, so it's not one and done kind of thing. The design evaluation, we need to combine simulation-based assessments with field commissioning tests throughout the entire project development cycle, but also lifetime of the project to make sure that any changes in design are reflected in the models, are studied as needed, and all impacts are captured. Specifically, she talked about how enforcement is important because for developer, the main goal is to deliver a project on time and bring it into operation. So if there are no requirements for design evaluation from the system operator, from transmission owner, the developer will do only up to what's required because that's what allows it to keep with its timeline. So require design evaluation, pre-energization, and as-built verification before commissioning if you want to verify that the plant conforms with applicable requirements during interconnection process and not after the fact. And then there is a need for internal expertise. Rishi talked about how there are a lot of consultants that are being involved, and then each of them understand only a certain portion of the project design, and there is a value in having in-house design evaluation capability that is supported by external consultants. All right, we are now in this second part of the meeting, so we felt like design evaluation is a big topic, and we need another meeting to talk about just that specific problem. So today we'll focus on independent system operator and utility perspective. So kind of like taking what was presented by developers and EPC contractors in the last meeting and taking it into, so what does the system operator need to require to make sure that this IBR plant design evaluation is actually taking place and happening. So we'll hear from MISO about their perspective on design evaluation. Then Jens Boemer from EPRI will present a little bit of an alternative way to do design evaluation. So I think in the previous meeting, we focused a lot on model-based and simulation-based design evaluation. So Jens will talk about what else can be done in this area. We'll hear from utility perspective from Anthony Williams from Duke Energy, and then kind of putting it all together, Ryan will talk about IEEE 2000.2 concepts and what can realistically be done as the IBR plant is being developed, kind of step by step look at putting all these pieces together, requirements versus what can be done versus what can be done with models, what can be done with documents. And then if time permits, as you see, we have 4 presentations today. We'll get to Q&A and structured discussion. We'll prioritize Q&A because I think that kind of provides for more lively conversation here. And so without any further ado, these are just some general rules of how we, how we drive these discussions here. And with that, let's go ahead and get started. And I turn it over to Alan from MISO to talk about ISO perspective and IBR design evaluation.
All right, thank you, Julia. Let me get my screen shared here and we'll get started. Okay, good morning. My name's Alan Urban. I'm an engineer with the resource utilization team here at MISO. Basically, that means I just deal with a lot of generator interconnections. I am talking to you this morning about MISO's proposed inverter-based resource modeling requirements. This is a set of requirements we had proposed at our stakeholder meetings in the interconnection process working group. And it kind of details what we're looking for in a modeling package from IBRs. So key takeaways here is this is going to end up being a business practice manual appendix for MISO. A lot of these requirements focus on just evaluations that could be performed during the interconnection process. And a lot of these tests just focus on high priority performance capabilities, not necessarily the full IEEE 2800 conformity. So it's basically a subset of things we're looking at. All right, so the focus of these modeling requirements really just are based on the model development at the plant level, design evaluation at the plant level, then as-built evaluations as well. We're not concerned about commissioning tests. We're not so much concerned about post-commissioning model validation in these requirements, nor are we concerned about anything happening at the unit level in these tests. Of course, we do care to some degree, right? So in our June interconnection process working group, we proposed a modeling package that would be submitted at interconnection application that consists of 3 types of models, but it ends up totaling 4 types of models due to software compatibility needs. That includes the standard library models, EMT models, and then UDMs, both compatible with TSAT and PSSE. Throughout the process, the interconnection process, we require all 4 of these models, all 3 of these models throughout the interconnection process, and the 4th one gets added on by the generator interconnection application phase. So it comes at the end. But these models get put under basically 17 model quality tests that are divided into 10 categories. They get wrapped up in a nice package, a good report's given with benchmarking, and that is submitted as the dynamic modeling package to MISO. So that happens anytime there's updates to the models at the interconnection application phase, and then all the way through to the GIA stage, as well as once these are commissioned, anytime there's an update made, we would require this same package be delivered again. So, all right, we're looking to implement these in 2026, so mid-2026. We got a little ahead of the 2800.2 standard. Big reason for this was we were trying to address a lot of these reliability concerns as soon as we can. And although we're probably not too far ahead of 2800.2, we're trying to get these in just a little bit ahead of 2800.2. So once 2800.2 is published, I think we're going to do a bit of a side-by-side comparison and decide on whether or not we need to make updates to these requirements. Or if we feel comfortable with what we have today. So, all right, so as we were developing these tests, we had to kind of strike a balance here between testing everything in IEEE 2800, which I think we were figuring was more than 70 tests, versus not having any modeling requirements, which I think gives us a very high reliability risk. And the approach we ended up taking here is just developing a subset of tests that we think are most relevant and useful. So. And what do we consider most relevant and useful? A lot of this was based off of a grid we developed here that prioritized different performance capabilities. You can see the ones that are in boxes here is really where we focused the most on. So tests were mostly developed to address those items on the left. On the right, this is more just kind of an FYI. This is how we adopted IEEE 2800 in our pro forma GIAs. Appendix G, it would be the portion that we're speaking of. You can see not every clause was adopted, but a good majority of them were. So, all right, this provides kind of a nice side-by-side comparison of what our tests are versus what's actually, or how they're associated with IEEE 2800 clauses. Ultimately, it's 11 tests, 10 of which are applied to every model that comes in, and then the 11th one, the phase angle change tests, is only applied to the EMT models. So. All right, I'm going to start going into the actual tests we run. There's not that many, so we can actually cover all these in this presentation. So you'll see exactly what we're looking for. Some kind of common test criteria and a few notes here. All these tests are required to be benchmarked. Every model is required to be benchmarked against each other so that we can see how different the standard library model might be from the UDMs and from the PSCAD models. This is all these measurements being taken at the point of measurement, which is the high side of the generator step-up transformer. That is our reference point of applicability. We identify, or we defined acceptable damping ratios to be 0.3 or greater, and that is, I think, right out of 2800. All these tests are performed on a single machine infinite bus. And then we also specified an SRC for the majority of these tests at 3. That was right on the line between what's considered high SCR and low SCR. And then the intention is that the SCR gets updated once we have an understanding of what the actual interconnection conditions are at that point of interconnection. So we can update it to higher than 3 if that's what's actually out there, or if it has to be lowered, that'll help us identify issues in low SCR conditions. So, all right, let's go into these tests. So our first one here is an initialization test. The main idea here is that we're just looking to make sure these models initialize and that they can flat run. We're also making sure that the reactive power can operate within specified ranges. You'll notice we have 4 tests here. 2 of them are specified at an active power of P-min. The P-min ones are only intended to address battery systems, energy storage systems. So P-min would actually just be charging or a negative active power effectively. Otherwise, everything else is tested at the P-max. So. We have a balanced fault ride-through test. The main things we're looking for here are that the plant, if it does enter momentary cessation, that it can resume current injection in no less than 5 cycles once the voltage recovers. And then active power recovery is also appropriate within a second of things coming back to the fault being cleared. So small voltage disturbance tests. On the right lower hand part of the slides here, you can see what we're specifying for the voltage at the point of measurement. And the idea here is that we're making sure the plant doesn't trip, stable and well damped response, that it's not entering momentary cessation, and then that the reactive power is doing what it's expected to do based on the control settings. So. Small frequency disturbance tests. Both high frequency and low frequency disturbances here. So this ends up actually being 4 tests, but only shows 2. So, each one is done with frequency getting stepped up and then frequency getting stepped down. The idea here is we're not expecting the plant to trip. Same thing as before. A lot of these all say similar things, must have a stable and well damped response. But we do this at 2 different states. The resource needs to be modeled at either 50% Pmax with no headroom. So the idea here is that the unit has no power availability above that 50% Pmax. So the idea is to kind of simulate just if there's not as much sun shining or there's not as much wind, the resource is going to be limited to how much active power can actually inject during these events. So we wouldn't expect there to see, if there is no headroom, an increase in Pmax from 50%. And then, of course, we want to model the situation where if you are just dispatched at 50% Pmax, but you have the availability to actually increase your active power, we want to be able to see that active power increase when needed. So, high voltage ride-through tests. Again, we're just testing to make sure this plant doesn't trip. Stable and well damped responses, and the momentary cessation is not occurring. So. Next slide here. Low voltage ride-through tests, same thing as before, making sure the plant doesn't trip, no momentary cessation. Any kind of active power recovery is appropriate once we're back to pre-disturbance values. And we step through a couple different low voltage dips here on the right-hand side. You can see what we're looking for. Frequency ride-through tests. We defined a slope of 5 hertz a second so that we're not accidentally tripping off on rate of change of frequency, but both for high and low frequency, making sure these plants don't trip. And then protection setting tests, we just have 1 high voltage, 1 low voltage, 1 high frequency, 1 low frequency test. And we do expect the plants to trip. I don't know if you can actually, is that in the way? There we go. But it's possible that relays might be set outside those operating conditions, and that is acceptable too if the relays are proven to actually be set that way. So, and then the last test that we put on all of the models is a short circuit ratio test, and this is not something that comes out of the 2800 standard. It's just kind of a common industry test. I think I don't know if it was Electronics or ERCOT that initially started doing this, but I know they both do this, and we felt it was valuable to include this one as well. So basically, we step through a number of SCRs to determine if the plant will trip or not. anything, we don't expect the plant to trip anything for any SCR greater than or equal to 3. Although we do specify tests below 3. This is more just to observe the response of the unit, but you would be considered passing otherwise if you were able to maintain if the SCR is greater than or equal to 3. So, and then the last test here is just for EMT models, is a phase angle change test. Again, just making sure the plants don't trip, and that they're stable and well damped. So also making sure that there's no momentary cessation. So we did also consider for just the EMT models a transient overvoltage test, but I don't believe 2800 touched on the transient overvoltage test, so we opted as well not to touch on that test. So originally it was part of our draft requirements, but we pulled it out before we started circulating it among stakeholders. That is all the tests that MISO is requiring. A reminder, these are still draft, however. We still have to bring these to a few more stakeholder meetings for feedback and comments, so there may be some updates to this. But we're hoping to get these published by Q4 of 2025, probably towards the end of the year, the end of that quarter. As an FYI, we're also exploring some tooling options to help automate these tests and automate benchmarking in the reports for this. It'll make basically processing all of this information a lot easier for us. We have some very large queues in the MISO queue if you're not aware. And then we'll start touching on comparison for with 2800.2 here for any possible future revisions. So that is all I have. I think we were taking questions at the end of all the presentations, but I'm looking forward to the discussion. So thank you.
Thank you, Alan. And yes, we're taking questions after the presentation. If you would like, you can put your questions in Slido using first 4 as the event code. You can see information right now in the chat. And so with that, we move on to Jens Boemer to talk about design evaluation learning and documentation review.
Yeah, good morning, good afternoon, everyone. Thank you, Julia, for the invitation. Thanks, Alan, for this overview. Great to see how you and other ISOs are adopting some of the concepts of IEEE 2800, specifically with regard to modeling. So I have about 10 minutes. I'll zip through a few ideas here. And just to remind folks, last month, I think I presented on particularly the modeling-related conformity assessments. So today I will focus a little bit more on the unit, IBR unit and IBR plant documentation. Now, to some extent, that fills this gap that we mentioned last month about the conformity assessment at the unit level, but it doesn't go anywhere towards certification. So just a reminder, there are no plans at this point to do any type of IBR unit or equipment certification for IEEE 2800. But nevertheless, I'll zoom out a little bit more here. These 3 terms, compatibility, conformity, and compliance, will still be important. Instead of focusing only on conformity, I'm broadening the perspective to also look at compatibility of equipment. And based on the structure and conformity framework of 2800.2, instead of only looking at the plant model development and the plant design, as last month, we are broadening the view to also include some type test and model validation and OEM documentation that comes along with that. As a quick reminder, most of those requirements of IEEE 2800 apply at the point of measurement. That's usually the high side of the main IBR transformer. There are a few that apply at the unit level. So that's the reason why modeling is certainly the best practice to account for all the ins and outs, how the equipment is designed and how the controls are designed, and that determines the plant's performance at the POM. But there might be good reasons why we don't always want to model everything. So that's the idea of today's presentation, to also look at what else can we do instead of only doing the modeling. A quick update here. I mentioned towards the end of the previous presentation last month about the IBR ID tool and also our forthcoming collaborative forum that would supplement these monthly i2X calls. Quick update on the tool for those who had not had a chance to engage with us on this. This can assess model quality across software and simulation domains, like do these models show similar performance? What's the applicability of a model? Is a positive sequence phasor domain model sufficient for the study? Grid forming behavior, the tool can identify grid forming behavior. It can help with generic model performance to address whether a generic model has been appropriately parameterized to represent the trend. It can also be used to assess performance against a requirement of a standard, for example, within the specified capability limits, and also look at model robustness. Just to give you one specific example here, and I'm not going to go into the details, the idea is to use the pass-fail criteria from standards like IEEE 2800.2, for example, to assess specific responses and give an output which of the criteria may have failed in order for the plant design engineer to better understand how to remedy. But today, we're going to look at the OEM and plant design documentation, which is also specified in clause 7.3.3 of 2800.2. In general, that includes a review of capabilities, review of settings, and review of equipment model validation report. So just the key message is IBR conformity assessment does not only have to be based on IBR plant modeling. As a reminder, we have this technology readiness that we're trying to track here from our side, and based on OEM's feedback, we have a list of issues with regard to the 2800 requirements that can be challenging for either new IBR units and even more so for some legacy IBR units. And many of you have seen these overviews. So that's something that we will see 2800.2 has also considered because it may not specify certain tests where it is known that either the requirement of the base standard is a bit challenging to meet, or tests are just not the right way to address and assess conformity. So for the first set of requirements that assess conformity with clause 4 of the main standard, this table gives an overview of how, for example, the applicability of requirements and registration of the IBR plant is assessed. That's based on coordination between the parties, and then IBR plant design documentation that may include a reasonable agreement on transmission network conditions during which the standard can be met, whereas outside of certain conditions, the plant may not meet this standard. So that needs to be documented in the IBR design documentation, for example. And we could go through each of those lines, which I will not do, but in general, both OEM documentation and IBR plant design documentation can be good sources for assessing conformity with these requirements. And depending on the level of detail, one might have to use non-aggregated single line diagrams to look, for example, at the reference point of applicability, whereas maybe some of the grounding might suffice with aggregated single line diagrams. Let's take a closer look at the consecutive voltage deviation right-through capability, because that is one that has gotten some scrutiny. The matter of fact is 2800.2 does not specify any tests for these requirements because the requirement itself is complicated. Models may not represent DC circuit or other important parts of the plant and the units, so they cannot produce meaningful results. And it can be impractical to test for different consecutive voltage right-through scenarios. So the idea is that 2800.2 requires verification be based on OEM documentation, including the type test results and the plant documentation. Now, there are some tests specified in 7.3.4.5 voltage right-through, but keep in mind that they may not be sufficient due to the mentioned reasons. For transit over voltage right-through requirements, the 2800.2 draft also clarifies that it may not be meaningful to do IBR unit type testing for transit over voltage right-through specifically because there are no pass-fail criteria in the sense that the transient over voltage envelope, which is specified at the point of measurement at the high side of the main IBR transformer, cannot be one-to-one translated to the IBR unit point of connection or terminals. However, what is useful is to assess whether a unit uses near instantaneous transit over voltage protection and document what those settings are, whether the unit uses active unintentional islanding protection, what surge protective devices are used within the IBR unit, and also what the OEM claims the transit over voltage withstand capability of that unit might be. And those that is documentation and information that can then be used in assessing the plant level conformity, where coordination between the transient over voltage capability of the unit and the surge protection within the plant needs to take place. So that is where documentation review may come in instead of any modeling. Now, coming here to the last but one slide, one big question is, when does it make sense to rely more on equipment performance and documentation, and when does it make sense to rely more on modeling? It's actually not an easy question to answer. It may depend on the grid conditions itself at which we want to assess conformity. Now, using documentation seems to be a faster path, but it also bears more risk, whereas modeling is really the recommended best practice path, which takes more time and effort and knowledge and resources, but it certainly reduces the risk at the end of the process. So comparing what this means in terms of the process, you may remember I showed this slide for the model-based verification last time. We can probably apply something similar here for documentation-based verification. It seems to make sense to review OEM documentation showing compatibility of IBR equipment and reviewing developer or generator owner documentation describing how the anticipated IBR plant design would address 2800 requirements early on in the process to create some confidence in the expected plant performance, whereas then towards the end of the process, a more detailed review specifically of any changes in that documentation seems to help addressing partial conformity with the standard. And with that, I believe I'm through. Thank you so much.
Thank you so much, Jens. Right, so let's go ahead to the next one. And we'll hear utility perspective from Anthony Williams from Duke Energy. Go ahead,
Right.
Anthony.
Thank you. All right, thank you. I'm Anthony Williams, Duke Energy, and I work in grid integration, and it's a wide-ranging group, but primarily the things I work on are technical interconnection requirements and also our design evaluation process. So I appreciate the invitation to speak with you all on that today. And just to touch on some of the items from last time, Julia did a good job reviewing them, so I won't go into a lot of detail, but we did some early pilots before we officially began our design evaluation process. And we saw a lot of those same things with, a lot of handoffs with the EPCs, contractors, some complications, sharing information across all those entities, on the developer side, but also just between the utility and the developer, just how you communicate requirements and requests and those things. And like Patrick talked about, we also see issues on the practical side of performance on the controls and just the numbers of settings that we have. So we wanted to try to build in some things to address those earlier on rather than just at the end at the commissioning stage. So so that's what we tried to do in our process, is incorporate those things and try to plug some of those gaps. So we think, well, we've seen the reports of performance issues and things like that in the industry, and we know some of the rocks to look under for performance issue, design issues. So we can say, oh, problem solved. We know where the issues are. All we have to do is fill those holes. So, but there's still the difficulty of implementing that process, and so that's kind of where we are right now. Is we have some guidance on how we want to review the plans. We have 2800.2 draft that also gives good guidance, and we're trying to build a process that takes us from like the interconnection agreement stage out to the commissioning stage. If you've been out west and seen the slot canyons or been in some, it can get pretty tight, and that's kind of how the design evaluation process feels to me right now. We know the path. We see like a narrow way to get from one end to the other, and we're trying to get that process in place to take us there. So we have some tools and some processes and things, and we just need to get the kinks out of them. And we know it's kind of like Alan was saying in his process with the modeling, there's going to be some things we can't get right away, but we think we can still get a lot of information right now, and then over time, we'll continue to add to it and improve the process. So real quick on our high-level goals. So our version of design evaluation we call CPR, or Capability and Performance Requirements Review. And what we want to do there is kind of get in early, right after the IA, and discuss those design requirements, make sure everyone's aware of our technical interconnection requirements, our CPR process, and we have several documents related to that, and some of them are core documents. We can touch on it later. They're posted on OASIS. We also have some supplemental guidance on special topics within the process to also help guide people. And then we also are trying a multiple review process throughout that design and construction timeframe rather than having one large design evaluation review at the end. We're trying to spread them out throughout the process. And so we hope that'll also align well with the developers and the EPC's normal design process. You know, our expectation is the things that we're reviewing are work products that are normally produced during the course of the design and the construction. And so, you know, passing them over to us for review or verification, we want to just be able to follow along with their process, work with any developer. And so, you know, have a structured process, but not necessarily a strict or a limiting process to where we can't adapt to each developer. And ideally, that would relate to reviewing tasks before some of the critical items are done. If, you know, many times these days, major equipment is ordered very early, but if we could get a review of that equipment early on, that can help and, you know, maybe prevent some missteps, things like that. So, and so in this presentation, I want to talk more about those things, the design evaluation piece. We know modeling is part of that. I'm a 12-year planner, so I'm very interested in the models as well, but we also want to kind of step back. And so as Alan's doing his tests in MISO and verifying all the models work right, we want to make sure that, you know, the plant's designed to meet those requirements, that design's verified, and then that actual design that you have in the plant makes it into the models that then get verified. So we're going to talk about some of those preliminary steps in defining what goes into the model. I won't spend too much time on this chart. I'll highlight a couple pieces, but this is kind of the core of how some of our goals are visualized. You know, at the top is the goal where we mentioned we'd like to, you know, review things early on. So, you know, over on the left-hand side, the blue curve just symbolizes that it's easier to make design changes earlier in the process, harder to make them later. And also the green line shows that impact is higher. So our process is built around, you know, starting early and trying to verify things along the way to try to prevent rework and, you know, other common mistakes. So the three bars right below that, you may not be able to read all these. Again, just from a concept level, just talk about how during a normal design phase, you'll have major equipment work, balance of plant, and then controls is a typical order, you know, general order of tasks. So those are the design tasks. And below the bar, the three bars, the horizontal bars down there is your construction piece. And so, you know, what we see just in the general process is those overlapping then, you know, sets the stage for rework if there's interconnection or requirement issues that are found, you know, having those overlap. So we try to encourage getting as much of the design work done ahead of time. And, you know, I know there has to be some. We're just talking about, you know, how to optimize. If we can move the design tasks more forward and get them ahead of the construction. And then just to illustrate the spacing of our design evaluation reviews, kind of the gold arrows that point upwards. We have CPR 1 on the left, right after the IA, CPR 2, 3, and 4. So those aren't mandatory reviews. Those just are symbolizing that we'd like to have a review early on for like major equipment, one later as the design's progressing one as the control equipment is being done, again, trying to space it out and review things as much as we can as the designs progress. So we're still struggling to get the process up to speed enough to follow along with every single project that we have. But again, that's the idea there versus, one large review at the end. We've done it that way. And, it's just back to the curve at the top there. We've done them at the end, but then, every problem you find is at the end of the process. So, basically you have to go back and repeat a lot of work to correct those things. And so we're trying to avoid that as much as possible. So in a review of our steps of how we've got here, on the far left, we have kind of a general structure of our documents. And I think what may be common to most utilities is the gray box on the left. We have our technical interconnection requirements. And then below that, we had a coordination document that kind of highlighted those issues and told people these are the kinds of things that we would like to review. But as we went through some preliminary reviews, we didn't get a lot of detailed information back from those requests. And so in the next version, we expanded the coordination document into like a design evaluation checklist as well. And that more gave a list of those plant and OEM items that we'd like to review. And underneath that, we had some supplemental documents that kind of gave more guidance into the different areas, like for PPC controls, inverters, things like that, of kind of a drill down, a checklist, very short, to the point. And so these other documents were explaining some more. They were too detailed, they were just kind of putting things in there as a placeholder, while the context was only for grid related and interconnection issues. They could read, as being very daunting. So in the third version, we kept the coordination document, but we've kind of combined or pushed those table of contents topics into the coordination document in the forms of data requests and questions about the design, so that people know the things that we're looking for. So, again, in the pilots, people would bring, what they thought we needed to review. We'd review those things and we'd say, no, we need these extra items as well. They bring those things, we'd review those, and we'd say, we need some extra items. So, I didn't really like the process of continually asking for additional documents and those things as we progressed through the review. So we're trying to refine the coordination document and the design evaluation checklist to where, we really have something transparent. These are the documents that we want to review that need to be submitted. And then they're also consistent. We can provide those very early on in the process. The EPCs, everyone else knows, these will be touch points. They're aware of documents that need to be provided, so they can do what they need to do to flag those documents, or boil them down into, summaries or something like that. So, and we do still have some guidance documents that just drill into a few more details. Those aren't requirements or anything like that, but it's in a way somewhat of a lessons learned type guidance, or providing more information on those particular topics. And so I think our process aligns pretty well with 2800.2. We talked about the modeling 732, and of course that's included in the design evaluation process. As we try to start early with the generic models. And then as we progress, we get updated and final models. So, those are definitely part of the process. But today we're focusing more just on the general plant, the general documents submitted. And so, as Jens touched on, those verifications in 7.3.3 of the OEM and the plant design documents. So a good section of our initial data request are just plant documents, equipment specifications, OEM documents on major equipment, ratings, how it functions, those kinds of things. And then we move into the more detailed work products with PPC narratives, inverter narratives, or descriptions of how those items work, and then plant studies, harmonics, reactive, and other studies, protection. And so those are listed in the checklist, so people know that we're looking for those, and those kind of provide the what's required to be submitted. The TIR, of course, is the overreaching document. So everything below the TIR is just there as an assistance to, again, be transparent and let people know the things that we plan to review. Ultimately, they need to comply with the requirements in the TIR. But, we get questions on how to do that or what demonstrates compliance. And so the checklist gives the what to submit. In the coordination document, it's more after you've submitted those things, what are we looking for there? What should the design include? And, within those documents, how should they show that they comply? So we're still working on all of these documents and trying to refine them into tools that work for everybody, whether it's the developers or the EPCs or even on our side as far as tracking the things that we'd like to review. So in the checklist, I just have a snippet here. It's nothing fancy about it. It's an Excel spreadsheet. The leftmost column indexes back to the coordination document. It has like an assessment item. And then in the blue columns off to the right, there's some X's to indicate the first time you might consider submitting this document. If you remember before, I talked about CPR being an ongoing process, and we don't necessarily have dates or required submittal times. We try to leave that to the individual plants, developers, and schedules that they have, and just more target, when that information is available, they can start sending it to us for review. And so, those preliminary plant and OEM documents should be readily available, very early. So we just call that generically CPR1, it'd be some of the first things you would submit. And then as the design progressed, if we think back to that timeline, we're going to have certain things coming following that. So those would just fall into CPR 2 and 3. So we try to avoid one-by-one submittals of information. We try to group things up as much as we can and have, larger submittals so that it's not so hard to manage, because managing the submittals is tough during the process. And our major divisions are generally those general documents I talked about, and then harmonic reactives, the narratives on PPC and inverters, models, protection, SCADA. So we track the project basically across those areas and independently on those items and kind of sign off each project as they go. Coordination document is a similar format, but it's structured a little more in like a question answer or a requirement response format. So it's numbered like the checklist. We have some requests for specific information. The customer can respond there in the column, and we can put our response there. Gives us a way to kind of track things. Again, the way our process is structured, we'll have multiple submittals, but this will give us one list that we can just carry across. Some people are concerned, when they see the whole list and they're like, well, we're not that far, we can't submit. And so, again, we're just trying to provide all the information up front, not that anyone would have all the information initially. And then we basically just fill this in as we go. And originally we started off with like a Word format. We thought, or specifically, I thought it might be more advantage to be able to, paste things into Word and make it more of a document. But people tend to want to manage everything in the Excel format. So we're switching to that to give that a try. And again, we have this list of documents that can be rather long. So that transparency and consistency objectives are a bit of a double-edged sword. So if you want to tell everyone what you plan to check, then the list can get exhausted pretty quick. So kind of striking that balance between telling people what you want to review and preparing them versus getting into too much detail in the documents is something we're still working on. But as we've gone through the process, to deviate a little bit just from the things that we've doing to some things we've learned is, we were seeing some rework items and having to repeat some work, things like that. And then also just kind of structuring it in my mind, like what things should occur before other things. I started to just map out some of the work products, some of the tasks that are done, and think about which tasks are dependent on other tasks. So I think I ended up around like 40 different dependencies between the boxes that you see at the bottom. The one below is a simplified version. But as I looked at the larger one, it seems, some started to kind of emerge as, to me, what seemed to be a little more critical task or ones that had more dependencies, more impact on the design. And so my apologies if you can't read the slide so well, but I wanted to just show you the whole thing on one slide. And it gets back to the point that we were kind of stressing earlier of separating getting more distance between the design side and the construction side. And so when you get the slides or afterwards, you can look at this some more, but the change notification piece is very early on, making sure we understand what's changed in the plant design since system impact study. And then the power quality study and then the reactive study are moved, way to the front, depending on each developer, work process, project, those things can occur at any time. But what we were seeing was the later that they are in the process, the more risk there was to the downstream items or maybe having to do rework and things like that. So kind of that last bullet is just, my thought is, as you're thinking of the tasks that are required to get the plant designed and constructed, is maybe just prioritizing those that, minimize the risk of downstream work. And so that's going to vary by, work process, of course. But as I thought about that, then, I've kind of laid these out based on, our experience. So, and we're sharing this now with our customers. So again, it's up to them how they do the work, of course, but just from our view, having things in more this type of order might, help prevent some rework or going back to do things. And just to close up on a few more observations. So as we've been implementing it, we've had quite a few revisions of the review documents. The design evaluation checklist is changed quite frequently. And so we haven't had that as a numbered document, but soon we'll have that up on OASIS as well, just because of the number of changes that we were making to it, trying to refine it with the individual reviews and those kinds of things. And I would also say to consider some topical documents to go underneath those that just help subdivide the information for the contractors, consultants, OEMs, things like that. So we try to break it into pieces where the developers can and the EPCs can pass along like a whole bundle of our information. They can break it into pieces based on who they're working with, but we're not having to rely on meetings and what people say in meetings or minutes or things like that. We're trying to get everything into documents that are easy to pass off among all the parties. We talked about increasing the time for design, getting that as far ahead as you can, trying to reduce the rework. And, right now we're still struggling with our process of the multi-stage CPR, trying to keep up with all the projects that we have in the queue. Each one's at a different stage of design, which means they're all at a different stage in the CPR design review process. So just managing all that, trying to keep the submittals from being, just continual submittals, but get them in larger batches so we can review groups of things at the time. That's taking a good bit of management, and then just how to reduce the review time on some items. I think Patrick touched on a little bit with the PPCs and how the designs vary, and it's the same with reactive power studies. Everyone does them a little differently, and so with those studies and PPC design documents, inverter settings, the sheer variety that's in those areas makes it hard to review those very quickly. So we're still working through and trying to think of ways that we can speed those up. And so our bottom line is we hope that these reviews will give us the proper configuration there in the plant. And we've seen a lot of success, I think, from the reviews that we've done so far in getting the designs and the work more directed towards what our requirements are. And so that way that plant performance is there when it goes into service. But then back to the models, once we've verified all those things, we've got it built in, done all the tests, then all that information can then get recorded into the power system models, so that we know that the models we have aren't just good models, but they actually are the best representation that we have of what's in the field. So that's all I had. So thanks for your time.
Thanks so much, Anthony. And so we have one last presentation, kind of to wrap it all up. We heard about design evaluation, I think, from different perspectives, both from sector perspective, meaning system operators, utilities, and last meeting we heard from plant developers and EPC contractor. So Ryan now in his presentation kind of bring us back up to the bigger picture and how it all fits together, how design evaluation fits together with the rest of the interconnection process and why are we even talking about this, and then dig deeper into some of the best practices to do design evaluation. So Ryan, go ahead.
Awesome. Thanks, Julia. Can you hear me okay? Just want to check.
Yes. Loud and clear, and I can see a screen too.
Great, cool. Yeah, thanks everyone. Ryan Quint with Elevate. And that was a really good set of presentations by Alan and Anthony and Jens. I think we didn't even really coordinate, but I think the presentations actually flow really well. So yeah, as Julia mentioned, my goal is to try to bring this all together, right? So a lot of what we heard were, lots of details around each of these topics, right? So Alan talked about, hey, there's modeling and simulation studies we can do to check to make sure the proposed project complies with the requirements. From a model perspective, that's a big part of what the transmission planners are doing for a living. Then Jens also talked about, well, there's documentation and there's other ways to do verification, and that's an important step. We can't forget about that. We can't just trust the models without additional steps to make sure that those models are accurate and the plant is designed the way it is stated to be, right? And then Anthony talked at the end there about, yeah, and what we see is that doesn't always happen, right? And we heard that at the last meeting from Rishi and from others that, yeah, there's a lot of complexities to that. There's a lot of room for error. So my goal is to try to tie that all together and talk and kind of look to, okay, well, where do we go from here, right? And I think it was Alan that said, if we adopt 2800.2 tests flat out, we've got hundreds of tests, and we're going from 0 to Olympic athlete in one swoop. And it's not really feasible. And so what do we do in the interim to get ourselves there? I think we all have the aspirational goal of having this process that is comprehensive, but also doesn't slow down the interconnection process, right? So first thing I thought I'd do is, okay, well, what are we trying to achieve here, right? What are the key goals and outcomes that we're looking for? We want clear and harmonized requirements for newly interconnecting IBRs. I think the transmission side, we know the transmission side wants that because they want to have a set of defined performance expectations. But I think the developers also want that too. Just tell me what I need to do to get through the process and try to make that like everybody else's, so that I'm not having to do a bunch of work or extra rework to comply with one region and then have to learn a whole new process for the other region, right? So the clarity and the harmonization of those requirements is really important. We want the IBR plants to then be designed to meet those requirements. And as Rishi mentioned last meeting, that requires contractual obligations, engagement with EPCs, engagement with OEMs, but we can't point to any one entity and just say, hey, do this, figure this out for me, right? It requires coordination on the developer side. We need models that accurately reflect that planned or as designed or as built facility so that we can run studies to make reliability decisions. And we need those various models to match each other. And so a focus on benchmarking is needed, right? So all of that work, again, is to ideally have a streamlined interconnection process, minimize the amount of back and forth that we have, minimize the amount of errors and the slowdown, and ideally have trust and confidence that we're making good reliability and study decisions, right? It's a heavy lift, but that's the goal or the outcome that we're trying to achieve from all this, right? We all know this. There's been various events that have really highlighted a lot of this for various years, many years now. And I think we're seeing it kind of come to fruition with this concept of how do we implement .2. I did want to draw attention to, there have been some NERC alerts and reports on this specific topic. And we talked about this, I think, in the season 1 edition of i2X first, but NERC issued a level 2 alert back in June 2024. They released a report in April 2025 highlighting what they found in that alert, and that alert was focused on IBR model quality issues. That report came out, and then the very next month, coincidentally, not so coincidentally, right after the Spanish blackout, Iberian Peninsula blackout, they issued a level 3 alert focused on both IBR performance and IBR modeling. A lot of what's in these documents is exactly what we're talking about here today. So I just wanted to reemphasize that there are some Euro enterprise level recommendations coming out from the regulatory body on these topics, right? So I'm not going to go through these in detail, but the level 2 alert from 2024 was really focusing on getting good models, getting accurate models, getting the various types of models, user-defined, standard library, EMT, building requirements, making sure those requirements are robust, clear, consistent, they include model quality checks, etc. And then the level 3 alert, actually, the reporting for that alert just closed a little over a week ago. So there's a handful of essential actions in the level 3 alert, some pertaining to the transmission entities, transmission owners, planners, planning coordinators, and then some essential actions for generator owners. And so a lot of attention getting put on having good, clear criteria, requirements, policies for technical details for IBR performance, enhanced modeling and study practices, model quality checks and model verifications, detailed reviews of the IBRs and their performance. And so all of this sounds like exactly the 3 presentations we just heard, right? But in a sort of a different flavor, but it's all sort of the same thing. So I've shared this slide before, and the way I describe the 2 standards is, or the 2 documents is IEEE 2800 is the what? It's the requirements. What do I need to do? How does this thing need to be the design? And then the 2800.2, which is the recommended practices, is the how. How do I build the plant and do all these steps to make sure that I meet the what? How do I meet the requirements, right? So that .2 recommended practice is very extensive, and I like to just reiterate what we hear from Andy and Yense all the time is that it's a compilation of existing practices today. So we shouldn't be sitting around waiting for .2 to come into existence for us to get started on this. So if you're an entity that's waiting either for the regulatory bodies or for .2, you're quite behind at this point. And I think we see that with a lot of entities now presenting on their practices, their requirements development, etc. And again, we just need to make sure we try to harmonize as much as possible. But I do think the big gap or issue that we have right now is, okay, we got the what, we've got the how, or it's in development of finalizing what the how is. How do we implement all of this stuff into the existing requirements, the generator interconnection agreements, procedures, business practices, facility interconnection requirements? All of those things exist, and as Anthony mentioned, a lot of that's up on Oasis. You can go find this material, or it's on the ISO's website and their business practice manuals or guides or what have you. But that is kind of a core focus of, and I think one of the bottlenecks is, okay, with all this stuff going on, how do I actually put this into effect? And that needs a lot of attention, I think. And right, so I try to again bring this to a very high level, but we've talked about this before. Step 1, and I even say step 0, is we need transmission providers to adopt IEEE 2800 and establish improved interconnection requirements that implement the standard. We've heard from the regulatory bodies, they endorse the standard, but they are not codifying or requiring the standard in any way, sort of verbatim or in reference. So there's different ways that entities can go about there. There's a great ESIG brief on this. There's various other materials. A number of us on the call here helped, write this document, kind of agree on, okay, there's all these different approaches, but there's a lot of ways you can go about this, and there's material out there that helps cover that. What I want to focus on is, this was in Jens's presentation, but a really good slide that Andy often shares, that there's all these steps in the .2 conformity assessment process, starting at the very beginning with, OEM unit level type testing, unit level model validation to make sure the model is reflective of the actual piece of equipment, the inverter, the turbine. Then we take all that verified, validated information, model, documentation, type test materials, and we build a plant model that's representative of the project. We then verify that, and we use that plant model in our IBR Plant Design Evaluation. And this is simulations and verifications to make sure that the plant is passing or meeting the obligations of 2800. And then construction happens. So all that's pre-construction, so leading up to and into the generator interconnection agreement. Then the plant gets built, and then you've got the as-built, what actually got installed evaluation. So this is a lot of verification steps to make sure, okay, what actually got put out there is what we thought was going to get put out there. And then there's all the commissioning stuff, right? So making sure that what actually got built and put into operation is behaving and performing the way that it should, and that the models end up matching what actually is out there in the field. So that's the post-commissioning model validation. And then there's all the operational stuff after that we're not really going to get into today. So really wanted to just highlight, those first two steps are typically completed by the OEM. And then those steps in the middle is where a lot of this interconnection process shows up, in terms of we need to conform to that process, but also implement some additional checks and balances. But all of that stuff there is really being done by the IBR developer / owner, right? And so we need some, like I said, checks and balances between the IBR developer and owner and the transmission entity, whether it's the utility or the ISO RTO, et cetera, to make sure that that's getting done correctly, right? So that's a key focus for me, at least, is that the steps highlighted there in yellow need to be somehow codified. Otherwise, they're not going to get done. We heard Rishi explicitly sort of say that last meeting, right? That unless it's an obligation during that development process, it's probably not going to get done. So in some ways, it needs to be codified. All of that has to conform to the new FERC Order 2023 interconnection process, the cluster-based system impact study windows. This is a great graphic from Lawrence Berkeley that just talks about all of that is now kind of consolidated and crunched down to much shorter windows of time. Now there is a notable amount of time from, say, signed interconnection agreement to construction to commercial operation, but the study process has been condensed. And so I think that's why we see, folks like MISO and Alan talked about this, that they're requiring a lot at the interconnection application phase, and then they're getting some things much later at the GIA, because between the interconnection application phase, i.e. the cluster request window, you immediately are jumping into studies and then making sort of decisions or updates about the projects leading up to GIA. So all of that's kind of been accelerated quite a bit. So we need good IBR plant designs and good models that match those designs relatively earlier in the process than we have in the past. And then 2023 and the ISO's implementations of that require actually that changes can be made later in the process, but they have to be documented, and new information, new models, et cetera, need to be provided so they can be evaluated. Step 2 of the process, and I think we've heard all the presenters essentially talk about this today, is that when the plant is getting designed, developed, working through that interconnection process, we need a way for the developer to build the processes to comply with those requirements, right? So that's establishing contractual language with the OEMs to make sure that the equipment that they're procuring is in support of conformity with the 2800 standard. There's coordination with the various EPCs. There's often multiple EPCs. There's third-party consultants running specific studies or some of the NERC requirements or building the models, et cetera. You have, the SCADA team, the inverter OEM team, et cetera. Then you've got the IBR plant and all the documentation that goes into that. There needs to be some version control of the various designs that are coming in. There's the models that get developed. There's version controls of the model, making sure that the models actually match the site. And then working those models through, okay, does the plant as designed pass the tests, right? And those tests need to be codified so that the utility, or so that the developer can say, okay, I know heading into the interconnection application phase that I'm going to pass their expectations. We still have a number of entities out there that want to get good models, but don't have any requirements of what good looks like. And so that's where a lot of back and forth and problems show up of, well, you didn't pass the test. Well, I didn't pass the test because I don't have information to know how to pass the test or what your expectation of the test are. So all of that needs to be trued up in the requirements themselves to make the developer, sort of enable the developer to work through that process more effectively. Without that, we've got roadblocks. So all of this essentially requires some type of repository, and so Jens mentioned a project they've got on the sort of the IBR plant database. We're also working on a IBR Plant repository in our GridStrong application. But so there's many ways to do that, but the documentation collection, vetting, version controlling is actually a much bigger issue than I think gets adequate attention. The number of times we come in to help build a model or help a plant meet grid code requirements or something, and the documents are wrong is staggering, right? The one-line diagram is missing the GenTie line, or the single line diagram or the controlled narrative is actually for a different OEM manufacturer, right? There's no one really checking this stuff until somebody's actually doing something with that documentation and realizing this is the wrong version. Like this is 6 years old and from the initial design, but now we're in the 90% design and no one updated most of the files, right? So it's not a human problem, I think. I think it's a version and process problem, like a software and process problem that can be fixed with better ability to track this stuff as the project evolves, because we know, we don't like to talk about it, but the projects do evolve. That initial interconnection application, there's actually not a lot known about the project as it's going into the queue. Typically, there's no PPC OEM selected. There's often not even an inverter OEM selected. The site layout's not fully vetted. That happens at later stages, and the interconnection process allows for those changes to be made per order 2023. The third step in the process is that the transmission provider needs to have a defined process for verifying that the proposed projects comply with the requirements. And this is right up Anthony's presentation. You know, he was talking about kind of, well, early stage, but especially into like kind of the later stage designs. But I think throughout that process, having some pseudo-automated and effective way to run through the documentation, the models, the study, the simulation results, etc., and know that, okay, the material that's working its way through this interconnection process and getting handed into the systems impact studies is actually of good quality and complies with the 2800 standard is a really important step. And I think this is where we're all kind of focused on right now, is how do we actually put that into effect? So when we go through, I kind of mentioned this at the very beginning, but what we really need, I think, and this goes for both sides, for the developer and for the transmission side, is that we want to know that there's adequate proof that's been provided, documentation, models, simulation results, etc., that, you know, all the documentation is compiled, it's accurate, it's appropriately representative of the site. The models have been verified against that documentation. We've got valid IBR unit and PPC models. The IBR plant model as a whole passes the model quality checks. So is the model functional? Can we see certain flags or protections represented? Does it have the right compiler? Step increment times. Does it pass the tests? So does it pass the simulation tests like Alan talked about? Do the models match each other? Are they benchmarked against each other? And ideally, the model quality and the performance report is provided in a standardized format so that the utility or system operator who's receiving 400 of these and during one interconnection cluster window can easily tell, okay, do you pass or fail, not, right? We need to make that step easier, otherwise we're still kind of flying blind, right? So the IBR requirements that are being developed need to adequately address all these topics. We can't leave any of these topics out if we intend to successfully implement the .2 practices, right? So from a model quality assessment perspective, we break it down at least into 3 distinct steps. One is the site verification checklist, right? So does the model match the site? The configuration, the OEM, the ratings, the basic protections, etc. Does the model meet the quality checks? Like I mentioned, the version controls, the model documentation, the flags, the protections, those types of things. And then does it pass the defined set of performance tests if they exist, to know ahead of entering the queue, does my model meet the minimum level of performance? And then they're going to load it into the system impact study. And I may have grid interaction issues, but I need to know that I comply with a certain set of SCR requirements, etc. So, Alan presented a set of, I think he said 17 tests. We can sort of boil those up to, a defined set of tests that closely mirror the 2800.2 tests that are referenced, I believe, in clause 7 of 2800.2. So, and again, it's aligned very closely to Alan's presentation and other requirements that exist. Initialization tests, basic model functionality tests, balanced and potentially unbalanced fault ride-through simulations, small voltage and frequency disturbances, looking at the clause 5 and clause 6 type performance characteristics of 2800. You've got the voltage control and reactive power capability. So again, clause 5 materials, high and low voltage and frequency ride-through. So this is clause 7 checks, short circuit strength checks, protection verification checks, like Alan mentioned. So all of these are sort of taking the general concept of 2800.2 and the tests that have been listed out and sort of simplifying them down to, rather than checking 30 plus operating conditions using an aggregate and a disaggregated model, we're sort of saying, well, what we can do today with the confines of the 2023 process that has been defined is we're going to do a limited set of those tests. So we have some trust that the model is doing what we expect and want it to do, and it behaves the way that the requirements have specified under a specific set of operating conditions. When these performance tests are designed in a specific way, where in particular we're controlling the grid side equivalent, voltage source to behave in a certain way, then they can be easily automated, right? So when you add in plant reference set point tests and things like that, you now have to create hooks into the models, and that's relatively straightforward with the standard library models, but it's not so easy with PSCAD models and with UDMs. Now, engineers can do it, but completely automating it becomes rather difficult, right? But when you're just controlling the grid side voltage source, all of those tests can be automatable, right? And so there was a mention, I think Jens had mentioned that, there's this trade-off between verifications and modeling / simulations. And I would argue the modeling and simulation piece, most of the work is going into, do I have a good model? Do I trust the model? Is the model verified? Then I push the run button and I crank through the various regions performance tests that have been established. I select what models I want to crank, PSSE, PSLF, PSCAD, TSAT, etc. And I run those through a set of computers to run those simulations. I take all those results, I overlay them on top of each other. I compare those simulation plots to make sure I get one, a good response, and two, responses that match each other. And I populate all those simulations into a standardized report. Everything in this process is 100% automatable in terms of study, simulation runs. You push run, you go grab coffee or have lunch, depending on the length of the simulations, and you come back and your report is done, right? And so we're taking we collectively, we need to take the grunt work of running the simulations out of the chain here and focus on the engineering on the front end with the models and the back end with the simulation results. The simulation results, analysis of those results can also be somewhat automated, right? Now, having engineer oversight and monitoring of the results and what's coming out is always good practice, but pass-fail criteria can also be, defined and codified in the post-simulation analytics work that happens to know as I'm going through the report, I should quickly know, do I pass, do I fail, or does an engineer need to check it, right? And so we don't ever look at the greens, we don't ever look at the reds, we just look at the yellows, because the greens and the reds are easy passes, easy fails. And the yellows are, gosh, this one looks concerning, I should spend time on this. So the faster we can take a set of models and get our attention on simulation results that look concerning, the better, because we're spending more time doing engineering and less time doing grunt work. Southern has also released a set of model requirements. So this is just an example reference that I pulled off of Oasis, but they've also kind of put out a template for how they want their model performance reports to come in, right? So they've also got a checklist of what their model package looks like, right? So when you submit the model package, you've got to provide all this information, and they give you, okay, here are the file extensions, the descriptions of the versions that we want, etc. So this is really useful for the interconnection customer to know, okay, here's what a successful package looks like. And then they also have descriptions, and on the subsequent slide or subsequent page in the appendix, they actually have a example set of simulation test results. So they codify, we want the length of the simulation to be this long, we want the plots overlaid like this. So all of it gets really standardized, which makes the automation or the simulation tests rather straightforward to produce quickly for the interconnection customer. Last slide I'll just mention, and this is very much aligned with what Anthony was talking about, is I personally think that this post-generator interconnection agreement, the post-GIA, pre-COD, pre-commissioning phase is the wild, wild west right now. There's no standards. There's very minimal language or information in the generator interconnection procedures and agreements. There's no NERC standards, at least as of yet. And so it's really up to industry to do what they think is best. And this, I think, is a huge gap for the industry. We need transmission side review of the approved IBR plant design settings, etc., ahead of leading into commissioning. And so I agree with everything that Anthony said, but to sort of simplify it down, after you've signed a generator interconnection agreement, there is agreement that has been made that this is what's going to get installed. This is how that thing is going to perform. And you have a certain defined set of network upgrades associated with that. And when you veer off of that, you're no longer complying with that agreement that's been established, right? And so there needs to be some check of, okay, what actually is going to get commissioned or is getting commissioned matches what I thought was going to get commissioned. We can't wait years and years to find those errors during an event or during post-commissioning monitoring. So having some degree of oversight of the commissioning steps, the commissioning process, and the verification, having sort of an IBR plant verification checklist that gets rolled out for every commissioned facility, I think is a necessity and something we don't really do today. I won't say nobody does it, but many entities really don't have a process for providing some degree of oversight to how the plan actually gets commissioned, right? That oversight doesn't have to be a negative thing. It can be a collaborative thing, right? Because the utility wants the project to be successful. The developer wants the project to be successful. We're all on the same page here. We just want to make sure we all have the same information and everything gets done correctly. And there's some gaps there that sort of put us on the same page, right? So that trust that I think both sides are trying to develop is making sure that what gets commissioned matches the models. Anthony had a whole list of examples, but EPC documentation, single line diagrams, control narratives, protection settings, RDB files, models, unit level and PPC capabilities versus ASLEFs versus maximum capabilities and performance. And then there's all the other stuff, monitoring equipment, configuration, control settings, protection, SCADA, design, all that stuff needs to be checked because those are where the errors pop up, right? What we're kind of recognizing is that having dedicated and educated staff that are working on these steps is a needed thing and something that doesn't happen in most cases. So I think why is Duke sort of out in front of a lot of folks in this area? Because they've got folks dedicated to doing this. Whereas in many utilities, you may have one person that is doing it as a side job on top of their other job, or multiple people who are doing it as a side job. But we really need folks that are dedicated to going site by site as these things are being commissioned to just check to make sure everything was done right. I think that helps both sides, again, the customer, interconnection customer, and the utility, right? There is a NERC SAR on this topic, I will say, right? And it's been accepted by the standards committee. It's been assigned to a drafting team. So it's on that drafting team's to-dos to develop some requirements around this. But that work is outside of the milestone 3 work. So it gets a lower priority than the Order 901 efforts, but it is underway, just with a lower risk profile. Last thing I'll mention is post-COD, there's a bunch of NERC standards going on right now. So just for sake of timing, I wanted to highlight that the The milestone 3, mod 26, mod 33, mod 32, IRO 10, TOP3, all those standards revisions for the 901 milestone 3 projects, all those projects failed their initial ballot. That is not uncommon for the initial ballots to fail. I always like to highlight that. But the additional ballot voting period is upon us. So later this week into early September, that final voting period will be happening. After September 10, we'll get an update from NERC on how those standards did through the voting. And we're running out of time because it's all due by October and will be in mid to late September. So there will be a crunch time and the question everyone's asking is, will NERC have to invoke the Rules of Procedure Section 301 process to get passing ballots or passing standards if any of the standards don't make a pass on the next vote. So we'll learn more about that here shortly. So we should all be keeping an eye late September into early October on those standards projects that are listed up there. So I'll sort of skip the conclusions. I've already highlighted a lot of this stuff, but hopefully this helped just kind of package it all together. And yeah, I'll turn it back to you, Julia.
Thanks so much, Ryan. Okay, so let's maybe go ahead and take the questions first, and before we switch to the discussion. I've started in order kind of as people voted the questions as well. And the first one was to MISO. Would it be more efficient to shift the requirement for UDM benchmarking from the application phase to the pre-synchronization